Well, welcome back to General Relativity. Sorry it's been a bit, but I will finish this course in time. So today I'm bringing to you the results of me reading a few times, I suppose, Chapter 4 in Carroll. So let's get right to it. Basically, this chapter is about what are the equations of general relativity. In particular, what is Einstein's field equations, right? And so we're going to use the connections and the curvature and the Ricci scalar, all that stuff, now to write the equations of gravity. But of course, to set the stage, we first need to talk a little bit about Newtonian gravity because, of course, in some limit, we know that general relativity has to reproduce what we already have observed for a couple hundred years, right? So that's the first order of business. I'm just going to review Newtonian gravity a bit here. So suppose you've got a mass m at the origin and a mass little m. Well, then Newton's universal law of gravitation, as it's known, says the force is gmm over r squared in the r hat direction. So here I put the big mass at the origin and the little mass at position r. So gravity is attractive. It points along the points to the origin, right? And so if you look at that, that tells us that the acceleration would be minus gm over r squared r hat. And so in the same way you can talk about, the potential energy per unit charge, right, the so-called voltage. In electrostatics, you can talk about the gravitational potential here as well. So basically the force per unit test mass would be minus the gradient of this gravitational potential, all right? And so, let's see here. So it's not potential energy, right? Like it's potential energy per test mass or something like that. But anyway, so you got minus gm, g big M over r squared r hat is minus the gradient of this potential, which then tells me that partial phi partial r is gm over r squared, which when we integrate, we get phi is equal to some constant minus gm over r. And of course, near the surface of the Earth, right, where we've got the radius is the radius of the Earth plus the altitude, we can expand in the Taylor series like so, and get the familiar gm over re squared h. I would say familiar. That's actually not quite honest. Usually you see mgh here, right? But the little m is missing because, again, this is potential energy per unit mass. All right, just like voltage is potential energy per unit charge. It's like that. Okay. Okay. So anyway, there you go. And of course, if we use the constant, Newton's universal gravitational constant, 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared, and the radius of the Earth, which is about 6.37 times 10 to the 6th meters. And the mass of the Earth, which is 5.972 times 10 to the 24th kilogram, and you put all that together, you get 9.798 meters per second squared, which I, typically just sell as 9.8 meters per second squared to keep it simple. And so what we have then is that the potential of Newtonian gravity is about gh, where that g is 9.8 and h is the altitude, right? And so potential energy, on the other hand, is mgh. All right, I think I've said that enough. And okay, so what's going on here? Well, excuse me. So if we take the surface integral of the area over the surface of the Earth, that is going to give us gm over r squared r hat dot with r squared solid angle r hat, right? That's a formula for ds. And of course these dot product to 1, and you just get the integral of the solid angle over the Earth, which is 4 pi, because we're being simplistic here and saying the Earth's a sphere. Of course, it's a late spheroid or flat disk, depending on. Well, if you think the Earth's a flat disk, you're not listening to me by now anyway. So we'll throw that out. Sorry, flat Earth people. Find somebody else to learn general relativity from. But anyway, so the r squareds be canceling, and you get 4 pi gm. There's a minus. Yeah. On the flip side of things, and this is less obvious, you can apply. Well, I mean, applying Stokes' theorem is fairly obvious. It's an abuse here because Stokes' theorem, technically speaking, doesn't hold when the domain. Well, I mean, this diverges at the origin, right? So it's kind of bad form to apply Stokes' theorem in a volume where it diverges. But it turns out Stokes' theorem reasonably extends in the context of distributions. In particular, you can view the divergence of this very special vector field as 4 pi times a three-dimensional Dirac delta in this way. And you can think of this as just a notation for saying any integral which contains the origin, you get, a unity from it in some sense. If you want to see more details on what exactly this means and how to understand it, if you look at my Calc 3 notes, I've got a few pages on that. Not from the perspective of distributions and higher analysis, but just kind of what this means as a notational scheme. It's anyway, okay, so that's the Dirac delta function, which is technically not a function, but anyway. And so what you got there is the divergence of the gradient of the potential integrated over the volume, right? On the other hand, you've got, excuse me, and then on the other hand, you got 4 pi gm, right? So, and of course, you could think of m as being, I guess the thing that's missing here is m is the integral over of the density, right? So maybe I should add that to this to just kind of seal the deal. This is minus 4 pi g integral over the ball of radius r of rho, the mass density, d3v. All right, so since this and that are equal, it stands to reason that the Laplacian is equal to 4 pi g rho. Notice there's a minus here and a minus here, so we get plus here. All right? So there we go. This is, you probably haven't seen this before, but this is the analog of Poisson's equation in electrostatics for gravitation. All right? It turns out that we get a 4 pi g rho here. That's going to be important as we try to kind of calibrate the equations of relativity. So anyway, I think this is just a rehash of what I just did. Yeah, so we've got the potentials minus gm over r. You calculate the gradient of that. Then the Laplacian of that works out to 4 pi gm Dirac delta in 3D. But another way to look at this is that if you think about a point mass at the origin, that is in fact, mass times the delta is the formula for the density. That says that there's a mass m at the origin and there's no mass anywhere else. All right. So this is the density formula for a point mass, and that is the equation that we have here. All right. In contrast, I think it's useful. Maybe you're more familiar with electrostatics. Some of you, I know I am. And if we have, the electric field rather is the force over charge, then the electric field is minus the gradient of the potential, which again has the meaning of potential energy per unit charge. Gauss's law says that the divergence of the electric field is the charge density. Here, rho is dq dv over the permittivity of free space, which we call epsilon naught. And so then if we combine these two things, then we get minus we get the Laplacian of the potential is equal to minus rho over epsilon naught, and that is known as Poisson's equation. And on the other hand, we have Coulomb's law, which is this. And so that's the electric field for a point charge. The Coulomb field, as it's called, and here K is 1 over 4 pi epsilon naught. And so if you write the Poisson's equation in terms of the k, you get minus 4 pi k rho. So it's entirely analogous, right? Like it's just, they're really just the same thing, yeah? But what's the difference? There's a plus here, there's a minus here. Why is that? It's because gravity is attractive, whereas if you have like charges in electrostatics, it's repulsive, right? So they are very, very similar in terms of being inverse square laws, but on the other hand, they're quite different in that gravity is always attractive, whereas the story for electrostatics is a little bit more nuanced, right? All right, so then, how to find a law of gravity? Well, we use what's called the minimal coupling principle. And again, this is all from Carroll, Space-Time and Geometry, Introduction to General Relativity here. What is it? I don't know if it's the first edition, or this is like an international edition I think I've got, but I used to have a hard copy, but I lost it somewhere. Of all the books I've ever lost, that's up there on my list of sadness, because it's not cheap, the hard copy. But anyway, hardcover. Here we go. So law of minimal coupling, it's kind of easy. It simply says you take a law of physics valid in an inertial coordinate system in flat space-time, point number one. Number two, you write the law in a coordinate invariant form, meaning mostly with tensors. And then you just assert the resulting law holds in curved space-time with the appropriate adjustments, namely replacing the Minkowski metric by the curve metric and replacing partial derivatives with covariant derivatives. All right, that's how you do it. And, Carroll has a nice example, and here I'll share it with you. If you look at a free-falling, unaccelerated particle, then you that would be the acceleration 0, right? In usual Minkowski space, which is not quite a tensorial equation. I mean, the velocity is, but the second derivative is not. But you can convert it to a tensorial equation by taking one of your derivatives and doing the chain rule to convert it like so, and then you've got now it's manifestly a tensorial thing because you've got a contraction over Lorentz indices, and again dx mu d lambda. Well, that is a vector. All right. So, good news. To write that in curved space, we just replace the partial mu with the covariant derivative, which gives you this, which is exactly the geodesic equation. So in general relativity, free particles should follow geodesics. So that's kind of nice. So that's an example of the minimal coupling procedure, right? Okay. Now, let's see here. So this is going to take a little bit. Nothing in this lecture is really rigorous, all right? Because what we're doing is we're trying to explain the plausibility of physical laws, right? So from a logical perspective, you can pretty much just assert those to be true and then sort of describe how you should make contact with experiment of those equations, and then you do experiments, and if you make contact with reality to a reasonable approximation as governed by the ruling referees of physics and made up statistical standards, that sort of thing. If you make it past those referees, then voila, you got physical theory. But technically speaking, you don't really have to justify the basic laws of physics logically, and yet people don't really believe that because they always feel the need to justify the basic physical laws, so go figure. So let's do it. So, like I said, motivating equations of general relativity from a Newtonian limit. We're going to think about moving slowly, which means that the velocity is much smaller than the proper velocity is much smaller than the rate of change of time with respect to proper time. Also the weak field limit, which means that basically your Minkowski metric plus a little perturbation, this h mu nu, which is small in comparison to eta mu nu, which has got components of plus or minus 1 or a 0. And the gravitational field is static, no time dependence for g mu nu. In this context, we're going to study that geodesic equation, see what it looks like. All right. So, all right. So this is the geodesic equation for such a path. And let's see here. I said other terms are small in comparison, right? So usually this thing is contracted. There's like I and j summed over terms. If you go back to this here, right? This is a sum over nu and a sum over rho. In principle, though, there's an I. Those are sum over spatial indices. But we only keep the temporal term because in this we're looking at the limit where the temporal derivative, if you will, is much bigger than the spatial derivatives with respect to proper time. As such, the only thing of interest in the geodesic equation is this term. And so we can expand that. Here's the connection coefficient, the Christoffel symbol, right? The inverse metric contracted across the appropriate sum of derivatives of the metric, but remember, it's static, so time derivatives are 0. Only this one can matter, and even so, we get that, all right? But since g mu nu contracts to the Kronecker delta, it follows that you can write the inverse metric as Minkowski plus h, because when you multiply these two guys together, if you ignore higher terms in h, you just get back to Kronecker delta, which means that to this approximation to first order in h, eta plus h is the inverse of eta minus h, all right? Okay, so given that we know what the formula for the g inverse metric is, and so what we get then is let's see here. It takes me a second to sort through all these equations here. Let's see. I'm trying to remember. Well, excuse my coffee. Well. I mean, this is just what we got to, right? So I'm just, oh man, you can't see it. We're just using this equation in view of what we just learned about the connection coefficient, putting those two things together. We gets us to here, and then that implies that d tau squared is 0, because why? So since partial 0 h0 0 0, all right, and also okay, yeah, that's dumb. So this is different things for different choices of mu. So if we put mu equal to 0, that gives us d squared t d tau squared, and that's 0 because there's no time dependence to the metric, right? So that gives that 0. And then if we look at the spatial part, then that gives that comes back to this, which, sorry, I hope I'm not off the edge of the world here. So that comes back to this, which then becomes this, because that's just eta. Well, it's Kronecker delta ij plus h. And since we're only working first order in h, we ignore the piece with h would be second order, so we drop that. It just gives us this, which then gives us that apparently 1 over dt d tau squared times dx. So then I'm multiplying this to the other side, gives us this, and then I say that implies that dxi d tau squared is 1/2 partial I who. No one calls that who, but there's a reason for that. I derive it on the next page. It's basically a kind of chain rule thing. It's, you gotta be careful. Well, I don't know. Maybe careful is the wrong word. I guess, yeah, situational awareness, perhaps. So dxi d squared x dt squared is ddt of dx dxi dt, which by the chain rule would be d dt of d tau dt ddxi d tau. But then the thing is, we have from the zeroth component of the geodesic equation that dt squared d tau squared is 0, which means that dt d tau is constant with respect to t. So I guess technically I got to do another chain rule. Anyway, long story short, this pulls out. All right, that pulls out, and then you're just left with this here, which then you can do the chain rule again, and you get d tau dt d tau dt d squared xi dt squared. And so we've shown that d squared xi dt squared is equal to this. All right, the ith derivative of the 0, 0 component of the perturbation. And if you compare this to the formula we had from the Newtonian case, right, which was the acceleration, this is acceleration, right, is equal to minus the gradient of the potential, then that suggests that, in fact, the h0, 0 must be minus 2 phi, right, because there's a 1/2 here, and it's the ith derivative of h0, 0, so, if we differentiate minus 2 phi, then we'll get like minus the derivative of phi and then divide by 2. That gives you, derivative of phi, which is this, but then there's a minus, so. All right, so therefore, as we study the Newtonian limit, we find that the 0 in this weak field limit, that g0, 0 should be like minus 1 minus 2 phi. That's the relation between the Newtonian potential and the 0, 0 component of the weak field metric. All right. Now Einstein's equation, there's a story there to be told as well. So like the first and kind of most natural thing to try would just, and I guess from what I read, and Carol Einstein proposed this to start with, is just that the Ricci's tensor was equal to the stress energy tensor times a constant, right? That's kind of like one of the first things you might think about, because I mean they're both symmetric tensors, and it's just kind of a natural thing to try, but you soon give up on it because the covariant that forces the covariant derivative of the stress energy tensor to be 0. Well, that I guess this doesn't, but because of conservation of energy momentum, the covariant derivative of the stress energy tensor is 0. But then that makes the Ricci tensor covariantly constant, which then makes the Ricci scalar like proportional to the trace of the stress energy tensor, and then that means that the stress energy tensor's trace is constant throughout space-time, which is just not reasonable in terms of like physics, because the trace of the stress energy tensor is not constant in physics. Like it's just not matters not like that. It can be lumpy. So we had to try something more complicated, and it took Einstein a couple of years, but he came up with this, the Einstein tensor, as we talked about in previous lectures, right? This g mu nu, and which is the Ricci tensor minus 1/2 the Ricci scalar times the metric. This is a symmetric conserved tensor, and so we can at least attempt this. G mu nu is equal to kappa T mu nu, where that's the stress energy tensor. But the question is then, what does this coupling constant need to be? All right, and we'll figure it out by looking at the Newtonian limit. Again, as always, following Carol. So here we go. So just to recap, we got your G mu nu equal to kappa T mu nu, and that is R mu nu minus 1/2 R G mu nu equal to kappa T mu nu. And of course, you can also recast that. I think I'm trying to find it. I'm deriving an equivalent but also interesting form of this equation, all right? So let me just we need to finish this, then we'll get back to the problem of figuring out what kappa is, okay? So if we take the trace of this, basically contract against the metric, we get the trace of the stress energy tensor, we get the Ricci tensor contracts to the Ricci scalar, and that gives us apparently r is equal to minus kappa tau. And when you plug that back into the proposed Einstein equation, you just get this. If you solve for the Ricci tensor, you get Ricci tensor is equal to kappa times the stress energy tensor minus 1/2 the metric times the trace of the stress energy tensor. So it's kind of a neat equation, because what that means is that in the absence of matter and energy, where your T mu nu and your trace of T mu nu is 0, you'd get that the Ricci tensor is 0. And what that would mean is space is flat if it's away from matter and energy. All right. And, you know, full disclosure, we're not currently taking cosmological considerations into account in this comment, all right? In fact, we'll get back to some of those cosmological considerations here towards the end of this talk. Not too deeply, just a little bit, but we'll get back to it, all right? So the problem is to determine the value of the kappa from the weak field Newtonian limit. Towards that end, we're going to consider a perfect fluid source of energy momentum, which has this formula. So you have the density plus the pressure, 4 velocities, and then over here you got your pressure times the metric, right? We're talking about rest frame energy density, rest frame momentum density, actually. I said pressure, I think I meant momentum density, my bad. So we're going to neglect pressure in the Newtonian limit, since we're looking at dust, where essentially the rest energy is massive compared to velocity. So like it wins, and we just can worry about the rho times the product of the proper velocities there. And more than that, we can take the proper velocities and we can set them equal to 1 or minus 1, depending if you're talking about the contravariant or the covariant component here. Contravariant 1, covariant minus 1. And the reason for that is explained right here, sort of. I think it essentially boils down to our choice of units and things here. But anyway, since we've got the other velocities are 0, that makes this have to be minus 1, since like it is the Minkowski metric at a point, I guess. And well, anyway, there's some nuance here that I don't want to get into. Long story short, 1 and minus 1 for these. And so in view of that, we have T, let's see here. In view of that, we have T mu nu is this, which is either rho when mu and nu are both 0, or it's 0 otherwise. So in the Newtonian limit, T0, 0 is just equal to rho. And that's just much larger than other components. All right, so if we trace G mu nu against T mu nu, it just boils down to G00, T00, which is minus 1 minus H00 times rho, which is, dropping this tiny term, is equal to minus rho. Hence, we obtain that the Ricci tensor is kappa times T mu nu minus 1/2 G mu nu T. Really just gives us that R00 equal to kappa. The interesting part is R00 equal to kappa times T00 minus 1/2 the G00 times T, which, putting the things we just learned in, the T00 was rho, and T was minus rho, but notice you got this minus, the minus, which is G00. We're dropping the H00 since it's like, tiny compared to everything else here. So we're just keeping the minus 1 and G00. And then the T was minus rho, so you got 3 minuses. So that gives you 1 minus 1/2, which gives you 1/2 kappa rho is R00. But we also know, so we'd like to connect that to the metric. So we're getting there. And so R00 is, remember what it is. Well, it's the contraction of the Riemann tensor. lambda, cross lambda here like that. And but we know that when you put all zeros, it's 0 because it's anti-symmetric and some indices there, and that makes that 0. But so contract over I like that. And here's like before we contract over I, let's just look at what it means for I and j. All right, so if we just look at, let me zoom in a bit here. So if we look at I and j, by definition, that's this. And the thing is, remember we're looking at static limit, so that's irrelevant. And these we can also ignore, since if you look at them, they're like gamma gamma or gamma gamma terms, which are second order in the metric. And so like what's much larger in this limit is just this single gamma. And so all we need to do is look at the first term in this contraction, and so we do. And so what happens is down here, R00 is contract across I, which is really just contract this, just keep that first term. But then remember that this expands in terms of derivatives of the metric, contracted against the inverse metric like so. Again, static limit, so that's 0, that's 0. This is the only thing that matters. And so remember, that just gives us this H00, and Kronecker delta ij, partial I, partial j, and that is minus 1/2 delta, the Laplacian of the 0 component of the perturbation. Therefore, the Laplacian, well, the nabla squared here, H00 is equal to minus kappa rho. Now, where that coming from? That's coming from, remember, let me zoom back out here just a bit. It's all here, we just got to put it together. So up here we had R00. R00 was 1/2 kappa rho. Let's see here. And boop, 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 boop. But we also have that R00 works out to minus the Laplacian of the H00 component, right? So it's this, but it's also equal to that, so we get that. All right, but what else do we know? We remember we had that Laplacian of the potential was 4 pi g rho, and in that page 5 on these notes, we had H00 was minus 2 times the gravitational potential. So if you put this and that together, we get delta nabla squared of minus 2 rho is equal to, well, minus 8 pi g rho. But remember, so this is H00, and so we have either the Laplacian squared of H00 is minus kappa rho, or it's minus 8 pi g rho. So you can compare these and find out, voila, kappa is 8 pi g. So there we go. That, I would say, calibrates Newton's, rather, Einstein's equation. All right. So I know it's a bit much, but that's how we can learn that the coupling constant is forced upon us from Newtonian gravity in this way, and that gives us Einstein's. And again, in some, from some logical perspective, you could just say, well, this is basic, so I don't have to, explain it. But I mean, it should it's a reasonable assumption to say that new physics should reproduce old physics that we already have lots of experiments on, at least in some limit, right? And this does, in that sense, that we just went through. Okay, so Einstein's equation for general relativity is this. R mu nu minus 1/2 R g mu nu is equal to 8 pi g t mu nu. This is the Ricci tensor. This is the Ricci scalar. That's the metric. This is the Newton's universal law, Newton's universal gravitational constant, and this is the stress energy tensor. All right. We can also, much like we did a couple pages ago, we can rewrite this for as the Ricci as R mu nu is equal to 8 pi g times the stress energy tensor minus 1/2 the trace of the stress energy tensor times g mu nu. And we said this before using kappa instead of 8 pi g, so this is kind of a rerun. All right. So, great. Now, we just kind of, so this is basically the start of chapter 4, I think, in Carroll. And then he reproduces these equations from a variational principle. And then the later part of the chapter, I would say, is kind of a survey of a number of advanced issues in terms of how can Einstein's equation be modified or studied. All right, so just kind of give you a snapshot of where we're going. We're about to be much more sort of hand-wavy from this point further. Okay, guys? So there's also another way we could attack the derivation of Einstein's equations, which is through Lagrangian formulation. And this was, I think, in part due to Hilbert. Well, probably was mostly due to Hilbert. Hilbert saw that the only independent scalar that we could construct from the metric, which is no higher than second order in its derivative, is the Ricci scalar. And because of that, he said, well, the action has to be just the integral of the Ricci scalar then. And so if we study a variation of the action under small variations of the metric, then it suffices to actually study variation with respect to the inverse metric because they're tied together by this chain rule. And so if you study the variation of the Hilbert or the Einstein-Hilbert action, you've got three things going on. You've got the, goodness, why do I have three things? Well, oh, because remember the Ricci scalar is the contraction of the inverse metric against the Ricci. This is actually two things. This R is, G upper mu nu contracted against R lower mu nu. So there's really a product of three things here. And so you get a triple product rule. You get the variation of the Ricci tensor, the variation of the inverse metric, and of course the variation of the determinant of the square root minus the determinant of the metric. All right, so each one of these requires a different sort of tact. Let's go through it. Now, he actually has separated these into separate integrals, and that's probably better, but I'm just going to, you'll forgive me for being a little bit sloppy here. Okay, so I'm going to try to be brief here because really the point of this page is that when you study the variation of the first piece, after everything settles through, you end up with this, which integrates to zero. So that actually doesn't contribute to the Einstein equation. So basically the first piece, the variation of the this piece right here, it doesn't lead to anything for the equation. So it's kind of, yeah. All right, so anyway, there's that. Forgive me if I don't explain it all. It's just kind of formal calculus at this level in here since, yeah. And then he turns to to describe the determinant part. That's kind of a little bit more, there's some things there I could explain and perhaps they're interesting. So the natural log of the determinant of a matrix is the trace of the natural log of the matrix is a matrix identity, where the natural log of a matrix is implicitly defined by saying the exponential of the natural log of the matrix is the matrix again. So anyway, if we take the variation of the natural log of the determinant of the matrix, then, well, that's going to give us the variation of the trace of the natural log of the matrix. And because the variational derivative still behaves mostly like a derivative, it has like chain rule. So differentiate a natural log, you get 1 over the thing, right? Times the derivative of the thing, which in this case is the variation of the determinant of m. Trace is linear, so you can essentially pass the determinant inside, and when you do that, you get 1 over the matrix, but we write m inverse because it's a matrix, and then times the variation of the matrix. The fact that the calculus works like that, in part, is based on the fact that it's inside the trace where you have cyclicity of the trace. Otherwise, you'd run up against the non-commutativity of the matrix and its inverse in that derivative. But anyway, that's a can of worms I don't want to open here. In any event, so what all this means is that if we calculate the variation to the determinant of the metric, that is going to, which would be this, right? So just multiply determinant m to the other side, we get the determinant of the metric is what we call g, so we get g times the trace of m inverse delta m, where we're putting m equal to the matrix of the metric, which means m inverse is the matrix of the inverse metric. And so that gives us this. And therefore, if we calculate the variation of the square root of minus g by the chain rule, we get minus 1 over 2 square root of minus g times variation of g. But remember, the variation of g was just calculated up here to be this. And so when you got, something over the square root, you just get the square root, and you get a half out there, still there, like so. In summary, oh, goodness gracious. In summary, the variation of the Einstein-Hilbert action, the interesting terms are the, the square root of g pops out, and g mu nu delta, and so goodness gracious, I have to go back 2 pages. Sorry guys, give me a second. Come on, get. Stupid fingers. So again, this term, irrelevant. This term, nothing to do, that just appears in the answer. And this piece over here had an R right here, right? So the piece I just talked about with the log and the determinant and all that, that's this piece. Rats. And so that gave us this, because this guy and this guy, this is leading to this term, that is just from the original variation. And then this has to hold for arbitrary variations of the inverse metric, so it follows that r mu nu minus 1/2 r g mu nu is equal to 0. Now, that's not the whole story, because you notice so far there's no matter. So this is Einstein's equation for in the vacuum. And we need to add matter, so we do that. And when you add the matter term, you end up with basically the same variation, but now you've got the variational derivative of the matter part of the action. Excuse me. And so he defines this as T mu nu. That then gives us Einstein's equation. And so that's the variational approach to deriving Einstein's equation. And it's important, not so much for this course, but if you want to study theoretical physics more deeply, most theoretical physics is framed in a variational approach. And even to understand the last half of Carroll's chapter 4, it's wall-to-wall variational, the variational approach. I'm trying to keep this course a little bit lower level, so I would say that the last 20 pages or so of chapter 4 in Carroll are, he's talking about some really kind of sophisticated issues that I don't think part of that's, I think, a paper he wrote with a couple other people on the Kaluza-Klein theory, and that's interesting, but maybe not the right thing to look at for your first course in general relativity. So I would say read chapter 4, but don't despair if you don't understand the details towards the end, because it's pretty technical. So I'm just going to try to give us my goal right here in the next 5 minutes or so is just to summarize the central points of what he's saying towards the end of chapter 4. One of the main themes, and this is not in chronological order in terms of the book, right? I'm skipping around. But one of his big themes is scalar fields in general relativity. So what's a scalar field? Well, it's a field that doesn't really have any features to it. It's, you can talk about spinors. Spinor has spin, scalar doesn't. It's just kind of a plain featureless field in some sense. So like a Example of a scalar field in physics would be the Higgs field. So it's not that they're not interesting, it's just that um, they're like, you're like, well, is an electron a scalar field? Well, no. Is a proton a scalar field? Well, no. So anything you know from chemistry is probably not a scalar field. But anyway, a scalar field with potential V has these, this is its equations of motion. So now in curve space, the box is the contraction of the covariant derivatives. And so this is sort of the curved version of what's called the Klein-Gordon equation, I believe. And in this context, the energy momentum tensor ends up being this, and it's on page 164. He derives this. So here's what that looks like. All right. Now, what's interesting is that a lot of the modified versions of general relativity, which are of interest, basically can be viewed as like conventional relativity, where you've added in a scalar field. All right, so if nothing else, scalar fields are important to understand in terms of just modifying relativity. And so there's a whole family of these things called scalar tensor theories. And basically you've got these two extra terms, the function f times r, and this pure scalar piece, and then the matter piece in the action. And when you sort through that, you get these modified Einstein equations, namely the Einstein tensor is equal to this mess right here. And you know, this would reproduce Einstein's equation in an appropriate with an appropriate understanding for these different theories, and yet produce something new in another understanding. And there have been attempts to, like, theoretically, or well, experimentally detect the difference between conventional GR and these scalar tensor theories. And as far as I know, no one yet has been successful to prove that, you know, there is in fact a successful scalar tensor theory. But I might have missed something in the last 10 years, you know, so I don't take my word for it. It's you know, the next best perhaps hope for modifying general relativity a bit. And in some sense, well, let's just go on here. Well, the big one is the Brons-Dicke scalar tensor theory. I actually heard a talk on that one as an undergraduate, where basically the point of the talk was, well, we don't think it's physically observable yet. that was for what, 30 years ago, I think, 20 years ago for me. Probably the first technical physics talk I ever went to, actually, at Appalachian State, probably like 1999 or 8 or something like that. Probably 1997. Who cares? But anyway, these are modified Einstein equations. These tend to arise from string theoretic derivations of general relativity. So oftentimes, the scalar field somehow appears in like a more, in some sort of high energy theoretical physics. The scalar field appears, and it ends up sort of modifying the equations of general relativity a bit. Now, there are other ways to modify general relativity. As he mentions, you could talk about extra spatial dimensions. Kaluza-Klein theory, for example, is usually thought of as being extra small dimensions, so-called compactified dimensions. And then you can also, there's also these extra large dimensions, which I don't understand anything about. You can also add higher order terms in the action, and you could also look at non-Christoffel connections. You could actually suppose that, you know, like in some sense, this whole discussion, at the very start of everything, we assume we're working with a metric connection, right? So like, if there's something interesting to find there in having a connection which isn't metric, we're like removing that from the discussion at the outset, right? So I mean, you're used to this in like calculus 1. If you put the constraint in at the start, everything's 0, right? So maybe we're doing that with this as well. You know, like we're removing freedom that we shouldn't at the start because we think we understand what we're looking for. But anyway, there are experimental consequences of standard general relativity, and we have observed some of them. So whatever the modifications are of general relativity, it's very speculative, I think, at the moment. This much I will say, though, the cosmological constant. This is perhaps, maybe, well, not sure what's exactly the right way to think of this, but certainly Einstein is the original source of this. He put this constant into his, he realized that you could add a constant times the metric there, and that it would have, deep physical implications. In particular, if he put that there, he'd be able to create a static cosmology, which is sort of philosophically attractive to Einstein, because then you don't have to explain the beginning, right? Like, explaining why the universe had a beginning, it's kind of annoying if you don't believe in God. And so, yeah. So he introduced it, but then, it fell out of favor for decades. And I think it's only really been revived since around the time I was in graduate school, at which point, like large, cosmological, large-scale observations about the universe, there's a debate whether or not the cosmological constant is positive, is it negative, is it zero? I'm not really sure, honestly, folks. There's this whole discussion about dark energy and dark matter, and it is involved with this issue. I would just say I am personally very apprehensive about believing people who talk about this stuff with any kind of certainty. All right? So it is a freedom we have with this equation, and it does have consequences in terms of how we analyze the large-scale motion and history of the universe and its future. But the other thing to say is that this lambda tends to, like, where is it coming from? Well, the answer is usually from some sort of high-energy theoretical physics. This lambda is perhaps like some kind of field, it's a consequence of some sort of field and string theory or something like that. There's usually some kind of other side story which is producing this this lambda. And again, that ties back into the discussion of the scalar fields, right? Because scalar field theory could put that lambda there for a reason. I think Einstein originally just put it there because it was physically plausible. Should mention some other properties of Einstein's equations. A very important one to notice is that gravitation is nonlinear. Gravitons interact with gravitons. So like this is sort of a Feynman diagram of that, right? Like this, there's no diagram like this for photons. Photons don't interact with photons as far as we know. And so that's a significant difference. He also talks about, I can't say this name, but I'm going to try, Ray-Shidehuri's equations, and this is covered in some detail in Appendix F. It reduces to, this theta is a formula for the volume, all right? So basically this is the rate of change of the volume of a little region with respect to proper time, and it's equal to minus 4 pi big G, the sum of the mass. So this is the energy density, and these are momentum densities in the x, y, and z directions. And this led Baez to state, the expansion of the volume of any set of particles initially at rest is proportional to minus the sum of the energy density and the three components of pressure. So that's pretty neat. I mean, that expresses the idea that gravity is attractive in a local fashion with a dynamical equation. It's really quite beautiful. And so that Carroll tries to give you some sense of the importance of this equation and this kind of analysis to the study of singularities. He mentions, some really natural work by Hawkins and Ellis. There's a great book by Hawkins and Ellis written in the early 70s on these sorts of things. And I once was friends with an Indian student of relativity who had a very negative view of Hawking's, because I think basically maybe a lot of the work was really done by this guy, and then Hawking's has gotten a lot of the credit for it. But that's my suspicion. But I don't know. I'm not a student of Indian physics, so what do I know? But anyway, so that's one thing, and this is essentially equivalent to the Einstein's equation. So Einstein's equation says that hey, the volume of space is contracting in the presence of energy and momentum. That's, yeah, okay. And more than that, we should notice that Einstein's equations are in fact nonlinear partial differential equations, which are constrained by certain relations. First order differential equations between the Wild tensor and the given stress energy tensor. And there are also various energy conditions to consider, and you sometimes assume those to obtain physically reasonable solutions. And Carroll has this litany of terminology it gives you back in here, what, section 4.6 maybe. I'll just show you the picture. So partial differential equations, even much simpler ones than this, you could spend a lifetime studying. And so here's these pictures of the different energy conditions, and here's like a momentum versus energy density graph, and they're the weak energy condition, the null energy condition, dominant energy condition, all these different things. So to understand how to solve, the Einstein's equation, you have to understand those things. And I did think this result was interesting. He says, in particular, Hawking's and Ellis prove a conservation theorem. Essentially, if the energy momentum tensor obeys the DEC, the what was that thing? See, I don't even know it says over here, the dominant energy condition, and it vanishes in some space-like region, then it will necessarily vanish everywhere in the future domain of dependence. So in other words, energy cannot spontaneously appear from nothing, or can it sneak in outside the light cone? So I think that was kind of a neat result. So I don't know. I feel like I could almost understand it, but just to say that if you want to understand how to study solutions to Einstein's equations, they're difficult, they're nonlinear, and work is continuing to this day in terms of like the analysis of these problems. It's not at all easy. But anyway, so that's it for chapter 4. We're going to move on to chapter 5 next lecture, which is on the Schwarzschild solution, which is a little bit more concrete. So again, like the last half of this chapter really is a survey of many things, and so don't feel intimidated. Don't feel bad if you feel a little bit intimidated by the last 20 pages of the chapter. So they're pretty technical. Anyway, thanks guys.